We have already seen that graphs can be either undirected or directed, but there are other variations as well. Directed graphs that have no cycles are one variation. Graphs whose edges have associated weights are another. We begin with the directed acyclic graphs. Such graphs are often referred to with the acronym DAG. One important characteristic of every directed acyclic graph is that it implicitly defines a partial order. That order is defined by taking the reflexive transitive closure of the relation defined by the edges. Those closures ensure the reflexive and transitive requirements of a partial order. The third property required of any partial order is that it be anti-symmetric. That property follows from the fact that there are no cycles. Every condensation graph formed by the strongly connected components of any directed graph forms a directed acyclic graph, because the process of condensation reduces all the cycles to a single vertex. One important algorithm associated with directed acyclic graphs is to determine a topological order. A topological order is a linear or total order that preserves the partial order. That means that any vertex that precedes another in the partial order will also do so in the topological order. Software project management diagrams are a good example of a directed acyclic graph. They define which tasks must be done before which others. For example, coding a class would need to be done before it could be unit tested. A topological order would be an order in which a single programmer could perform the tasks. Typically, there are many possible topological orders for every partial order. Weighted graphs are another important type of graph. A weight is typically associated with each edge of the graph. In some cases, the weights can be coupled with the vertices. A graph whose vertices represent road intersections and edges the roads themselves would associate a weight with an edge. That weight would be the distance between the intersections they connect. In a project management diagram, the weights might instead be associated with the vertices. They would represent the amount of time required to perform that task. A minimum spanning tree is a subgraph that is a connected acyclic graph of minimum weight. It represents a way to connect all the vertices of the graph with the lowest total weight of all the edges. In many applications, the weights can represent costs, and so would represent the least cost of connecting whatever the vertices represent. There are several algorithms associated with weighted graphs. These algorithms are often referred to as greedy algorithms because they make choices based on the lowest weight. There are two greedy algorithms for finding minimum spanning trees. Prim's algorithm selects some starting vertex and chooses the edge of smallest weight that connects the tree to a vertex adjacent to the tree. Kruskal's algorithm successively selects the edge of smallest weight that does not form a cycle. It uses the disjoint union data structure to maintain the connected components of the subgraph at each step. Dijkstra's single source shortest path algorithm is one that we will discuss in more detail shortly. There are several algorithms for determining all points shortest paths. The Floyd-Warshall algorithm is one of them. Dijkstra's single source shortest path algorithm is one that might be used by any type of navigation system. As we previously mentioned, it is considered a greedy algorithm because it selects the vertex that is closest to the starting vertex. It produces a tree that defines the shortest path from the starting vertex to every other vertex in the graph. Let's execute this algorithm on the graph shown below. We take A as the starting vertex. B is the closest vertex because the length of the edge AB is 2. J is next because the path ABJ has length 3. C is next. The path ABJC has length 4. Then D enters the tree because ABJCD has length 5. H is next. ABH has length 6. G is next because the edge AG has length 7. Then I is added since ABJCDI has length 8. F is next. The path ABJCDF is 9 long. Then K, ABJCDK has length 10. And finally E, because ABJCDE has length 12. We conclude with a summary of software development applications for which graphs are an ideal data structure. Undirected graphs have many applications. The topology of connections in a computer network is one of the best examples of an undirected graph. The vertices represent devices and the edges connections between them. Next, let's consider directed graphs. Flowcharts were one of the first diagrams used for designing software. The vertices are statements, and the edges represent the flow of control between them. Once structured programming became widely used, flowcharts were no longer needed. Instead, structure charts became the next type of diagram used in software design. The vertices represent functions, and the edges the calling relationship between them. When object-oriented languages became popular, UML diagrams became the primary design diagram. In these diagrams, the vertices represent classes and the edges class relationships. Finally, let's consider weighted graphs. Large projects usually require a project manager who uses a project management chart. The vertices represent tasks that must be completed. The edges represent the dependencies between tasks, and the weights, the amount of time required to perform a task.